That's Stuart Nelson from Arcology Solutions, engineering the shell of a lunar Arcology, regolith-insulated roof and multi-layer transparent perimeter system. Stuart Nelson is a designer, well, he's one of the driving forces behind ArcologyX. He's a design and systems thinker focused on sustainable infrastructure and habitat design for extreme environments. The floor is yours, Stuart.
Okay. Yeah, there's a little bit of confusion between ArcologyX and Arcology Solutions. We're using both names. We're kind of transitioning right now. But yeah, so I'm going to talk about an alternative way to build lunar colonies, right? Just the shell of them. I'm not going to deal with any of the guts. Oops. So just to put this all in context, so my concept is to put, these are very large buildings, about say 500 meters on a side, big hexagons. They can be spread over the moon. They have maybe 20 to 30 meters of regolith on the roof that floats on top, and that keeps the air pressure. And then they have windows all along. So it's a way to live on the surface of the moon, but still be safe. And as you can see, they're kind of in threes. And so the concept is these could just be replicated and spread across the moon. Oops, there we go. So the problem, you know, we need to be able to scale. We want to be able to put a lot of people on the moon. This is mostly what I call the kids and dogs stage of lunar colonization. So, you know, when people are going to be, there are lots of people going there are kids, families, everything. So yeah, so again, my solution is a pressurized system, uses the regolith on top to create the air pressure, or to hold in the air pressure, and then with mylar, some kind of a plastic window all around the outside. So we use, you know, we use a lot of in situ resources. We have a very large indoor area that creates, you know, these park opportunities for livability, and it also provides passive safety. So for instance, if you get a breach, so for some reason you get a hole in the side of it, the regolith roof then can slowly collapse into the building. And so what that does, excuse me, instead of losing pressure, you lose air volume. And so you maintain pressure until the roof gets all the way down to the ground. So that gives people time to either repair the breach or exit. So I'll talk a little bit about, you know, a little bit more about the concept, do some basic engineering analysis, and so on. As has been mentioned before, of course, there are the radiation hazard, micrometeoroids, thermal extremes. So lava tubes, yeah, I think they are a very good solution, especially for earlier stages. But for people who want to be able to look out the windows and see what's going on, they can be psychologically confining, and they are site specific. Although I learned today that there are many places for, you know, where the lava tubes exist. So a little bit more about the architecture. So there'll be a flexible membrane that you will pile the regolith on top of. And this creates like a blanket, basically. And again, it's on the moon, it's going to be fairly thick, like on the order of 25 meters. And around the perimeter, there are vertical supports. These will be like basically concrete rectangular walls facing outward that hold up the edge of the perimeter. So when you're first building it, it'll be deflated, or if it does deflate, around the perimeter, those are rigid walls and they hold up the edge. And then in between the perimeter walls, then there are mylar windows, and I'm going to sneak in a little picture here just to make it a little clearer. So these would be the perimeter supports, basically these rectangular walls that go inside and then hold up the roof. And then in between them would be mylar, which of course is going to be curved to reduce the forces required to hold in the air pressure. Not necessarily mylar, but some flexible material. And then the advantage, I mean, one of the big advantages is you're using up a lot of the lunar regolith. Also, I'll mention this later, but another big advantage is the lunar dust problem is always an issue. And so when you build this building, you're going to need all the local dust. And so basically you're going to clean all the area around your building, and it'll be a relatively dust-free environment then. So the solution then to the lunar dust problem is to put all the dust on the roof and use it as your blanket, and then you don't have to deal with it. Your machines that are operating outside locally to you, they don't need to worry about dust anymore. And then of course that one of the big advantages, you get this large volume, large interior volume without structure. So since the roof just floats there. And of course it provides you, shielding from radiation. So it's more than enough shielding for the radiation. And it also will protect you against micrometeoroids and actually pretty significant meteors. And as mentioned before, passive safety and breaches. So here's some basic information about air pressure and regolith thickness. And so this is a comparison between like Earth gravity, Mars gravity, and lunar gravity. And so you can see at the top of the scale here, this is Earth sea level air pressure, 1 atmosphere. And so if you want to have 1 atmosphere, you need 35 meters of regolith on the moon to balance out that air pressure. It's unclear exactly how much air pressure we need or want to live in. So that's, in some of the presentation, I've used like a half an atmosphere. So I'm not sure that's feasible. The highest on Earth, the highest continuously occupied town is La Rinconada, and it's at, it's at 0.67 atmosphere, so people live there all the time. But I assume, if you up the oxygen concentration, you have more control over the environment on the moon. On the moon, you can play with these numbers a little bit. Everest is at 0.33 atmospheres, the top of Everest, that's not really habitable. But inside of a spacesuit, they operate at 0.3 atmospheres, so they're just using more oxygen. So it's really the partial pressure of oxygen is the key issue there. And then, and you can see on Mars, the problem is simpler because you don't need as much regolith because you have 3/8 of Earth's gravity instead of 1/6 on the moon. And then on the Earth, I've included the Earth in here because I'm proposing that we also build these on Earth, right? We can build the same structure on Earth. And then, of course, the air pressure is going to be the delta. So if we, if we want to go 0.2 atmospheres above local, then we need, approximately a meter of dirt on top of our building to maintain that. And here's another, some basic engineering analysis of how much mylar do you need. So in here, this is based on, again, a half an atmosphere. So how much, this is the thickness in microns of the material that you need to withstand the air pressure. And this is, so and across the bottom is the span of the window. So basically, it's going to be a relationship between the span between the vertical walls and the air pressure. So if you go to a 1.55 meter span with Mylar, then you can do 3 layers of 20 mil Mylar. And these numbers are all derated based on NASA specs, things like that. So now, if you move up, there's been some research. I think it was done before 2022. I don't know exactly when. They're called 2D polymers instead of, because like Mylar is a 1D polymer, it's a long polymer chain, but it's possible to build polymers that operate in 2D, and those materials can be quite a bit stronger. And so if you have a 2D polymer, which is not really available yet, but at some point in the future it would be, then you're in much better shape. This is a 6 meter span with just 2 layers of this 20 mil polymer that has that strength. Now, in terms of the safety, so if you get a passive breach, this is the curve that shows, well, how much time do you have? And so this is assuming an edge length of 500 meters, an interior height of your roof of 30 meters, and an air pressure of half an atmosphere. And I picked this point, which is at 50 square meters. So if you assume you have a 2 meter wide windows and 25 meters tall, and you lose a whole section, that would be 50 square meters. And how much time do you have before the roof touches the ground? And it turns out to be about 15 minutes, almost 16 minutes. And so that's a pretty big breach. So if you can see this, the bottom axis is a log axis. So you have a lot of time for most small breaches. It won't be an issue. So the other thing is when I'm looking at this safety wise, you would want to build these in triplets. So you would want to have 3 that are close to each other, probably connected by tunnels. And so then you have a place to evacuate to if you need to evacuate. It doesn't do any good to evacuate if you're on the moon. By the way, that's one of the advantages of building them on Earth first, because you can get all this technology sorted out, and if you need to evacuate, you can just go outside. The other thing I thought about when I was looking at this is that you could also build tunnels, air tunnels between the 3 co-located communities, and so you could actually triple this you could take the air from the other communities and run it through a big air tunnel to support. And then you have 3 times as much air to evacuate, and so that number would go up. But probably, you would have some kind of a relatively automated repair mechanism for breaches for security. For meteor protection, when I was doing this analysis, I realized that really the issue is going to be the shock wave that happens, because the 25 meters of regolith is going to stop most meteors, but even if it stops it before it goes all the way through, it's still going to generate a pretty big shock wave inside, and that could be dangerous. And so I wanted to just take a look at how likely that is to happen. And so I did an analysis assuming that we have a lot of these spread out all over the moon. So there's 100 square kilometers of these building roofs. And the analysis comes out that, it isn't very likely that you're going to get, it's like hundreds of thousands of years between events that would have a significant, that would create a significant enough shock wave to actually injure or kill people inside. And presumably that, if you have 1,000 of these, you're going to have, you'll be able to detect meteors coming. and either bump them off course so they don't hit you, or worst case, evacuate the building before they get there. So the livability, so the idea here is that you have a very large structure. So the whole, my vision is the whole inside is just a giant park, basically, with some agriculture, but basically a big park. And so you can tell the kids to go out and play, and they can go out and play. They can go outside and play. And so that large area has hopefully will have a significant psychological impact on people living there. You do get a little bit of natural light from the outside, but that doesn't really help you in the lunar night. But it is nice to be able to look outside. And again, like this is the kids and dog stage. So for in situ research, let's see, just for constructing, I'll go through this kind of quickly. So, the process would be you clear the site of all the loose stuff on the surface. You seal this big area. You lay your roof membrane down and you build your perimeter supports. And then you deposit regolith, again, by cleaning up. You just basically clean the whole area all around. And one of the things that on the moon, because you don't have air, then you can use something like a snow blower to just get the air to move the regolith, because it's not going to be, you're not going to have any turbulence as it goes through the air. So if you get something moving in the right direction, it's going to keep going and land where you want. And then after you get that on, then you install all your Mylar windows and you seal it up, and then you inflate it. Now there's a lot of stuff that is available, but carbon and nitrogen are really rare on the moon. But I realized, actually I was talking to a friend of this, and a friend about this yesterday after we talked about it, and he was like, well, yeah, there are meteors on the moon. They're all over the place, and you got carbonaceous chondrites, and so in terms of so you can do asteroid mining basically on the moon, because you have asteroids that have already fallen there. And so on Earth, about 4 to 5% of the meteors that come in are carbonaceous chondrites, and so of course they have a lot of carbon and nitrogen, stuff like that. So that would be the first. That'd be one of the sources of carbon and nitrogen, and probably the first ones is you just mine it on the moon. And prospecting is pretty easy, because you just look for the big circles and you go to the middle and start mining, right? You don't need anything super complicated. Although finding out which ones are carbonaceous chondrites versus the other types of meteors is complex. You can also then, maybe the next stage would be importing stuff from Mars, like a mass launcher goes up Olympus Mons, which is 22 kilometers high, so that you don't have an air pressure problem. It's not going to slow down the stuff that's going out the end of the linear accelerator. And of course the gravity is lower, so that it's a lot easier to get things from Mars to the moon than it is from Earth to the moon. And then, you need large quantities. You can go out to mine the asteroids eventually. So comparison with other approaches, yeah. Got to make it look good for my product. So, but yeah, it has a lot of advantages. So yeah, and like I've mentioned before, the goal is to get thriving communities on the moon. And then of course we want to build analogs on Earth, but with the way I look at it, we don't want to just build a few analogs on Earth. We want to build a lot of them, because then we want people to actually live in them, and prefer to live that way. And that's it also makes it a lot easier if somebody's going to make the transition from moving from the Earth to the moon. If they've already lived in a habitat, it's much easier transition, right? If they lived in a basic lunar base, but it just happens to be on the Earth, it's easy to go. Plus, they get experience with all the internal systems, running the bioreactors and all that kind of stuff, right? And then, of course, multiplanetary, right? Living this way prepares us to be a multiplanetary species. It's another advantage, by the way, of this technology over lava tubes, because there are a few lava tubes on Earth, but mostly they're not available for us to live in because they're tourist attractions, but they're not very many. And so with this technology, we could build bases that were very similar to what they would be on the Moon or Mars, and build them on Earth. So this is just kind of a reiteration. I do have a paper on this that's in progress, so if anybody's interested in this concept and wants to contribute to the paper, it's up on GitLab. It's it's available, so you can look. In addition, there are I made several Jupyter notebooks to generate those graphs, to put in the equations and stuff. So there's Python code that generates the graph, and so those can be expanded, and we can add more detail to the concept that way. A few credits. Okay, so that's it. So any questions?
Chris?
Two questions, actually. First, you're using the Mylar windows. How well does that hold up under ultraviolet radiation?
Well, yeah, there are a couple things. One is there are Mylars that you can embed ultraviolet, like reflective stuff in them, so they do not degrade, or they degrade very, very slowly with ultraviolet. But the other big thing is that mostly they're going to be in the shadow, because you're going to have your regolith roof is going to extend over. So you have a long eave, because so most of the time they're going to be in shadow. The only time they're going to have sun is when the sun is really, really low on the horizon. Because you need the roof to protrude so that you protect the people who are inside near the windows from the radiation environment outside.
Okay, but you're still getting reflected ultraviolet from nearby hills, what have you, and since there's no ozone layer, and because of course the window fails, that's a big leak right there.
Yeah, so DuPont has a product right now that basically doesn't degrade with Mylar. They embed, I don't remember exactly what the material is they embed in there, but it gets a tiny bit yellowish looking, but not very much. So that technology exists to make Mylar UV resistant, or basically as good as, probably not as good as glass, but pretty damn good.
So Stuart, I found it interesting that you measure atmospheric pressure using atmospheres. I approve of that. Can you just comment on that?
Yeah, well, it's it's just a lot easier to communicate that way, because everybody knows what 1 atmosphere is. I mean, we have a visceral feel for it.
Right.
I know when the scientific community would like to use other kinds of units.
So you prefer that to pascals?
Well, like internally, if I'm doing engineering stuff internally, I would convert it to Pascal.
Yeah, I like talking about it in atmospheres.
Yeah,
no, I think that's good to use atmospheres. So good. And beautiful drawings of the lunar surface with the pods. Is that what you call them?
Yeah, I don't have a good name for it. I'm not a real name person.
No, I like it. Well, pods. Yeah. I think pods is a pretty good name. And then you do have the sky. With the lava tubes, you would have the sky. I can't think of the word now. The holes, and I've got it in my chat, but you know what I'm talking about. The holes in the lava tubes.
Yeah. Yes. Yeah.
The skylights, that's the word. The skylights. Yeah, it's a beautiful picture. No, it's very realistic, and it makes it appealing.
Yeah, well, thanks to AI for that.
Okay, well, or whatever. No,
You
really,
couldn't do that.
it's
Yeah,
actually
the
a
AI could.
it's actually a masterpiece.
No, thank you.
Something can always be improved, and nothing's all encompassing, but it's very, very very illuminating. I didn't mean the pun, but it's beautiful.
Thank you. So, any more questions? Especially the lava tube guys. I'd like to hear from the lava tube guys.
Yeah, I think the lava tubes that's really exciting. And it's not one or the other. You combine it. The lava tube, that's a gigantic breakthrough when you start to think of it.
I've been in a few lava tubes, and they're terribly, terribly irregular. I mean, you get big areas and small areas, and a lot of these for tourists,
You
they've
need
built
engineering like
steps.
this, try to even things out.
Yeah.
Yeah, no doubt you're right. There'd be a lot of work to do, but it's the backbone. It's the frame, and somebody was we just need the mortars. One of the presenters was saying it much better. Yeah.
Well, the ones that I've been in have been the result of volcanic activity, and
Well, that's what this is, isn't it?
And then people have said, well,
Wait a minute. First of all,
these
where
are
have you
from-
been in the lava? Where have you been in the lava tubes? Just so I understand. In Idaho?
South America, and there are also several in Washington State.
Okay, interesting. But I mean, okay, good. So, but the lava tubes on the moon, the lunar lava tubes, they're also the result of volcanic activity, right? I'm asking that question.
Yes. Some of them are also the result of impact melting, creating the lava tubes. So
Would that give a different type of structure?
Good
I
question.
don't think that it would, but I'm not sure that there have been any studies actually put into it.
But that's right. Okay, but whatever. One way or the other. More or less, a lava tube is a lava tube. It's a structure. It's the whole. Framework and the railroad. Somebody was explaining. I don't remember their words. It was very good. That presentation was very good. Also, look at that. That's beautiful.
Hawaii has a lot of lava tubes.
Yes, you can get an idea of the size of lava tubes by going to the Apollo 15, NASA Apollo 15 description. The Hadley Rill is a collapsed lava tube. I think it's like 60 kilometers long. And it's a huge structure.
So I just want to make sure on each pod. So the pod is a hexagon.
Yeah.
Okay, good.
Yeah.
Now each edge of the hexagon is 500 meters, right?
Yeah, it's just I mean, it can be whatever length you want.
Okay, good, but that makes sense. Okay,
yeah, but
so
approximately.
I just want to understand the dimension. So if that's 500 meters, so from one point to the other, I think I've done this correctly. I asked AI also to check it. It's 1,000 meters from one point to the farthest point, right?
Correct, a kilometer across.
Good,
Yeah. from
good.
point to point.
No, you get a
Corner
good
to
sense of it. It's sort of like a football field or some kind of athletic field. It's like it'd be a good unit of measurement in and of itself. Like you say, it's a pod.
Yeah, and they can be made bigger, but
Right.
but it's there's good. It's good to have multiples rather than large ones. For
No,
security.
multiples. No, multiple.
Yeah.
I agree. Just like is shown in the drawing. In the drawing,
Yeah.
if I'm counting right, I'm seeing 7 of them in the drawing. If I'm not missing any.
Those are big, and I think that's a conclusion there.
Yeah, they're big. Yeah.
Thank you for that, Stuart, and Max and Stanley.